I want you to picture something for a second.
Mm.
Imagine you are on a grueling, steep hike.
Okay.
You're trekking up this massive mountain, pushing through incredibly dense, high-altitude terrain.
Yeah.
Like you are sweating through your clothes.
Right. That's a real workout.
Yeah. But you aren't in the Alps, and you aren't in the Himalayas. You are in Mexico, or, maybe East Africa.
Yeah.
Or even on the island of New Guinea.
Which already feels out of place.
Totally. And you push through this final stretch of tropical or subtropical forest. You come over a rocky ridge, and suddenly you are staring at a massive ancient wall with solid ice.
It completely breaks your brain's expectations of geography, honestly.
It really does.
Because finding a towering glacier in a place we inherently associate with, intense heat and equatorial climates is just a jarring visual.
It feels like a glitch in the Matrix. But it's actually a perfect entry point for what we are exploring today in this deep dive.
Mm-hmm.
Because today, we are taking a comprehensive look at the cryosphere, which, it sounds like a term from a sci-fi movie.
It really does.
But our mission today is to unpack exactly what this frozen world is, discover how it functions as the Earth's critical thermostat, and most importantly, understand why its rapid transformation affects your daily life, no matter where you live.
Right. Whether you're next to a glacier or in the middle of a desert, it matters. And the term itself gives us a pretty big clue about its scope.
Okay, let's hear it.
So it comes from the Greek words kryos, meaning cold or frost.
Right.
And sphera, meaning globe. So it's basically the umbrella term for literally everywhere on Earth's surface where water is in a solid form.
So when people hear that, they immediately picture, like, penguins, polar bears, the North Pole.
Naturally.
But as our mountain hike in Mexico proves, it is so much broader than that. We're talking sea ice, snow cover, glaciers, ice caps, ice sheets, and, frozen ground like permafrost.
Exactly. And the sheer scale of it is just difficult to wrap your head around because currently the cryosphere covers about 10% of the entire Earth's surface.
10%. Wow.
Yeah, it's a massive portion of our planet locked up in solid water. And because it's so vast, it isn't just sitting there passively. It is this integral, highly active machine that drives the global climate system.
Well, I want to dig into how it does that.
Yeah.
Because 10% of the Earth covered in ice doesn't just, look pretty. It's doing heavy lifting.
Oh, absolutely. To understand the mechanics of how it regulates the climate, we really have to look at the physics of snow and ice.
Okay.
There are two vital physical properties at play here. The first one is surface reflectance, which scientists call albedo.
Okay, so think about walking across black asphalt barefoot in the middle of summer.
Ouch, right?
It burns your feet because that dark surface is absorbing almost all the sun's heat. So albedo is like the opposite of that, right?
Precisely.
Yeah.
Yeah, albedo is the ratio of reflected solar radiation to incident solar radiation.
Put that in English for me.
Basically, when solar energy hits the Earth, non-melting, snow-covered surfaces have exceptionally high albedo. They reflect roughly 80 to 90% of incoming solar radiation right back out into space.
80 to 90%.
Yeah, only a tiny fraction of the sun's heat is actually absorbed.
That is incredibly efficient. It's like having a perfectly white, highly reflective roof on your house in the dead of summer.
Right.
It just bounces the solar energy away before it can even heat up the attic.
That's a perfect analogy, and that's just the first property.
Yeah.
The second property is thermal diffusivity.
Thermal diffusivity, okay.
Right, which is a measure of how well a substance transfers heat through itself. And it turns out snow and ice are incredibly poor at transferring heat compared to air.
Really?
Yeah, they are many orders of magnitude less efficient at it.
Wait, why is that? Because you think of ice as freezing cold, so you'd assume it makes everything around it cold, too.
You would think so, but it comes down to its physical structure. Think about a layer of snow. It isn't just solid water. It's mostly trapped air pockets, and those air pockets prevent heat energy from moving freely. So snow and ice actually act as powerful physical insulators for the ground and the ocean below them.
Oh, I see.
Like if you have a layer of sea ice, it essentially decouples the ocean from the atmosphere. It blocks the heat and moisture in the relatively warm liquid ocean from escaping into the freezing winter air above it.
Okay, so going back to the house analogy, the albedo is the perfectly white roof reflecting the summer sun.
Mm-hmm.
But the low thermal diffusivity is like taking that same house in the freezing winter and wrapping the whole thing in thick fiberglass insulation. The ice Keeps the heat trapped exactly where it needs to be.
That is a brilliant way to visualize it. And when you combine the white roof and the fiberglass insulation on a planetary scale,
You get a thermostat.
exactly, you create incredibly complex climate feedback loops. The cryosphere isn't just reacting to the weather, it is literally manufacturing the weather.
Walk me through exactly how a piece of ice manufactures weather, because that sounds wild.
Okay, let's look at the Asian monsoon. When you have a particularly heavy winter snowpack across vast areas of Eurasia, it leaves behind incredibly moist, cold soils in the spring.
Okay.
Because that bright snowpack reflected so much solar energy away and insulated the cold ground below, the air sitting above Eurasia stays freezing and dense.
And cold air is heavy.
Very heavy. That dense, heavy air creates a massive, high-pressure dome, and that dome literally acts like a physical atmospheric wall.
Wow.
So months later, and thousands of miles away, when the warm, moist summer winds from the ocean try to blow northward to create the monsoon rains over India and Southeast Asia.
You hit the wall.
Exactly. They interact with those atmospheric pressure anomalies. A heavy snowfall in Siberia can physically alter wind patterns and moisture transport across an entire continent.
That is mind-blowing. White snow in Russia alters the summer rain in India just by being reflective and insulating.
It really drives home that the Earth is a single, interconnected machine.
It totally does.
Totally.
But, that Eurasian snow is seasonal. It melts. What about the ice that never leaves?
Ugh, the deep cryosphere. The timeline here is staggering because we experience snow as a seasonal event, right?
Yeah, winter comes, snow falls, spring comes, it melts.
Right. But the residence time of a water particle in a glacier or an ice sheet operates on deep geologic time. In many mountain glaciers, water might remain frozen for 10 to 100,000 years.
10 to 100,000 years.
Yeah. And that's just the mountain glaciers. If you go down to the deepest parts of the East Antarctic ice sheet, you are looking at ice that has an age approaching 1 million years.
1 million years old. That water froze into ice long before modern humans even existed.
Literally a time capsule of ancient atmospheres.
That's incredible. And in terms of sheer volume, 99% of all the Earth's glacial ice is locked up in those two vast ice sheets, right? Antarctica and Greenland.
Yes, 99%. But that remaining 1% of glacial ice is still a colossal amount of frozen water. And it's spread out across mountain ranges all over the globe.
Like we mentioned earlier, the Andes, East Africa, New Guinea.
Exactly. But the absolute powerhouse of mountain glaciers is Pakistan.
I have to say, I was completely caught off guard by the numbers on Pakistan in the sources.
Oh, the Karakoram and Himalayan ranges there are extraordinary.
Yeah, Pakistan has more glacial ice, over 7,000 known glaciers, than any other country outside the polar regions.
It's massive.
7,000. But wait, hold on. I need to stop and ask a fundamental question about glaciers themselves.
Sure.
Because you just referred to glacier ice, and scientists actually classify glacier ice as a form of solid rock.
They do, yes.
But by definition, a glacier is a body of ice that constantly moves and flows. Rock doesn't flow. So what am I missing here? If it's solid rock, how does it move?
It's a great question because it really bends the mind to picture rock flowing like a river.
Exactly.
It comes down to immense crushing pressure. The sheer mass of a glacier creates such intense internal stress driven by gravity that the crystal structure of the ice actually begins to warp. Yeah, it undergoes what's called ductile deformation. So deep within the massive body of the glacier, the ice essentially creeps forward like a super slow-moving, incredibly stiff plastic.
So the top is brittle and cracks, but the deep interior is like oozing down the mountain under its own weight.
That's the gravity-driven creep flow. But there's a second mechanism, too, called basal sliding.
Basal sliding? What's that?
Well, down at the very bottom of the glacier, where billions of tons of ice meet the bedrock, you have geothermal heat radiating up from the Earth.
Okay.
Combine that heat with the intense friction of the moving ice and the massive pressure actually lowering the melting point of the ice, and you get a thin layer of liquid meltwater at the very base.
So it basically creates its own slip and slide.
Yes, exactly. The water lubricates the bedrock. So the glacier is both deforming internally like plastic and physically sliding along its wet, lubricated base.
Does make so much more sense now.
And it's incredibly fortunate for us that these glaciers exist and function this way, because together with the ice sheets, they hold roughly 69% of all the fresh water on Earth.
Everyone, just let that sink in for a second.
Right, yes.
69% of the water we rely on to survive as a species is currently solid rock. slowly oozing down mountains or locked up at the poles.
It really highlights the fragile reality of our water supply.
It does. Now, while those mountain glaciers are ancient and slow, the ice floating on our oceans is basically living on fast forward.
Oh, absolutely.
The seasonal shape-shifting of sea ice is wildly dramatic, but the sources point out that it behaves completely differently depending on which pole you are looking at.
Yeah, geography dictates everything here. Let's compare the Arctic and the Antarctic. So sea ice forms simply by the freezing of seawater.
Right.
In the southern hemisphere, down around Antarctica, the sea ice experiences colossal seasonal swings. In February, during their summer, the sea ice shrinks to a minimum of around 3 to 4 million square kilometers. But by September, in the dead of winter, it explodes outward to 17 to 20 million square kilometers.
Wait, it multiplies its size by 5 in a matter of months. It basically builds a temporary floating continent of ice around Antarctica every single winter.
It really does. But if you travel to the northern hemisphere, to the Arctic, the seasonal fluctuation is much, much smaller.
How much smaller?
Well, it only varies by a factor of 2, going from roughly 7 to 9 million square kilometers in the summer to 14 to 16 million in the winter.
Why the massive difference? Why doesn't the Arctic explode outward like Antarctica does?
Just look at a globe. Antarctica is a massive landmass entirely surrounded by a limitless open ocean. The ice can expand outward in all directions without hitting anything.
Oh, I see.
Right, but the Arctic is the exact opposite. It is an ocean entirely confined by surrounding land masses. North America, Russia, Greenland, Europe.
So the land physically acts as a wall, stopping the ice from expanding any further south during the winter.
Exactly.
That makes total sense. The ocean ice is physically trapped. But let's look at the land in the northern hemisphere during winter, specifically the snow cover.
Okay.
Because in January, northern hemisphere snow covers up to 46.5 million square kilometers. In terms of pure surface area, seasonal snow is the largest single component of the cryosphere.
And this specific component is where the abstract science directly intersects with human survival.
Absolutely.
Yeah.
Think about the water coming out of your tap right now. If you live anywhere near a major river basin, there is a massive chance that water was locked inside a frozen mountain peak just a few months ago.
Yes.
These mountain snowpacks act like a gigantic global savings account for our water supply.
Where winter weather makes the deposits.
Exactly. Winter storms lock all that precipitation up as solid snow high in the mountains, safely stored in the cold. Then, as spring and summer roll around, the warming temperatures slowly withdraw those funds.
It's beautifully efficient.
It is. The melting snow steadily feeds the rivers, streams, and groundwater reservoirs right when the valleys below are experiencing their driest, hottest months.
It really is a perfectly calibrated natural reservoir system. It holds the water when we don't need it and releases it exactly when we do.
And the numbers on this are staggering. Over 85% of the annual runoff for the massive Colorado River Basin originates specifically as snowmelt.
85%. Wow.
Yeah. That single river feeds agriculture, powers hydroelectric dams, and provides drinking water for tens of millions of people across multiple states.
Which is wild to think about.
Without the slow release of that seasonal mountain snowpack, that entire ecosystem and economy would instantly collapse.
Which really highlights how precarious our reliance on this frozen water is. But, from the highly visible snow on the mountains, we also need to dig underground.
Yes.
To uncover the invisible pillar of the cryosphere. The frozen ground.
Permafrost, the hidden gem.
Exactly. Permafrost is defined as soil, rock, or even underwater sediment that continuously remains below 0 degrees Celsius, that's 32 degrees Fahrenheit, for 2 years or more.
Now, 2 years is the technical minimum, but much of this ground has been frozen for epochs, right?
Oh, absolutely.
Yeah.
The oldest permafrost has been continuously frozen for around 700,000 years.
Wow.
And its footprint is enormous. It underlies roughly 15% of the entire northern hemisphere. We're talking about 18 million square kilometers stretching across vast tracts of Alaska, Canada, Siberia, and high mountain regions like the Tibetan Plateau.
It's crazy because if you look at a picture of the tundra, it just looks like barren, frozen dirt.
Right, nothing special.
But underneath the surface, it operates like a giant prehistoric chest freezer.
That's a great way to put it.
Because for millennia, plants, animals, roots, mammoths, all this organic biomass died and got buried in the soil. But because the ground was literally freezing, that organic matter never had the chance to rot or decompose.
It just went into deep freeze.
Exactly. So you have hundreds of thousands of years of carbon-rich organic material perfectly preserved in the dirt.
Which makes tundra soil one of the largest carbon sinks on the planet. But here's the mechanism that has scientists deeply concerned.
Okay.
As global temperatures rise, this prehistoric chest freezer is effectively having its power cord unplugged.
The permafrost thaws.
Yeah.
And when a freezer thaws, things start to rot.
Exactly. As the frozen soil warms up, the biological processes that were paused for millennia suddenly restart. Microbial decomposition begins.
The microbes wake up.
Yeah, billions of microscopic organisms wake up and start feasting on all that thawed, dead biomass. And as a natural byproduct of their digestion, these microbes release greenhouse gases.
Right.
Depending on how wet or dry the soil is, they exhale either carbon dioxide or methane.
And because CO2 and methane trap heat in the atmosphere, they warm the planet more, which thaws deeper layers of permafrost, which wakes up more microbes. Wait, let me jump in here.
Sure.
Because whenever permafrost emissions make the news, the headlines always frame it as this apocalyptic sudden death scenario. Like it's a ticking time bomb that's going to trigger runaway warming and boil the oceans overnight. Is that actually what the sources say is happening?
It's crucial to separate the headlines from the actual atmospheric physics here.
Okay, good.
There is widespread consensus among experts that the emissions from thawing permafrost will not be large enough or sudden enough to trigger an unstoppable runaway warming scenario.
Oh, okay.
It is not an overnight doomsday bomb. We need to be clear about that.
Okay, so we can dial back the apocalypse a little bit. But it is still a massive issue, right?
A profoundly massive issue. The current understanding is that annual permafrost emissions over the coming decades will be roughly equivalent to adding the total annual emissions of a large, highly industrialized country to the atmosphere.
Wait, really?
Yeah, we are talking about an impact comparable to the total annual greenhouse gas output of the United States or China or Russia.
So it's essentially like a brand new, super polluting nation has just materialized out of the thawing dirt.
Basically, yeah.
It won't instantly buoy the planet, but it makes the global math of trying to reduce carbon emissions significantly harder to balance.
Exactly. And that unplugged freezer is just one symptom of a much wider system-level shift. When you look across the entire cryosphere, the transformation driven by warming is incredibly rapid.
Let's connect the dots on that wider decline because the numbers in the deep dive are sobering. Start with those mountain glaciers we talked about, the ones providing the drinking water.
Right, so the retreat of mountain glaciers is perhaps the most visible indicator of a warming world. If you exclude the massive ice sheets, the total global mass lost from mountain glaciers over just a 26-year period from 1993 to 2018 was an estimated 5,500 gigatons.
5,500 billion metric tons of solid ice just melted away into the oceans in a couple decades.
Yes.
And speaking of the oceans, let's talk about the big ice sheets and sea level rise.
The Greenland ice sheet is highly vulnerable right now. If global temperatures continue to rise to the point where the entire Greenland ice sheet melts, that single body of ice holds enough water to increase global sea levels by approximately 7.4 meters.
7.4 meters, that's over 24 feet of sea level rise.
Yep.
24 feet physically reshapes the map of the world. Coastal cities, agricultural deltas, entire island nations would be permanently underwater.
And the West Antarctic ice sheet is showing similar vulnerabilities. Its eventual collapse could add several more meters to global sea levels over the coming centuries.
It's just a staggering amount of water. Finally, let's look back at the sea ice, the shapeshifter floating in the Arctic Ocean.
The Arctic is where we are seeing the most dramatic, accelerating transformation. The extent of Arctic sea ice is declining at a rate of roughly 4.7% every single decade.
Wow.
Since we first started taking satellite records, the summer ice has declined by over 50%.
And projections suggest the Arctic could see entirely ice-free summers before the year 2050, right?
Yes. Which brings us right back to where we started, albedo, the white roof.
Oh, right. Because when you lose millions of square kilometers of bright white sea ice, you expose the dark, deep blue ocean water underneath.
Exactly. It's like taking the white roof off the house and painting it black.
Man.
The dark ocean absorbs the solar heat instead of reflecting it back to space. The ocean water warms up faster, which melts even more sea ice from below, which exposes even more dark ocean water.
It's a vicious cycle.
It is. This is known as the ice albedo feedback, and it is a powerful, self-reinforcing driver of regional and global warming.
We've covered a staggering amount of ground today. We've explored million-year-old ice caps, solid rock that flows like plastic prehistoric microbial freezers, and the reflective white roof keeping the planet cool.
It's a lot to take in.
It is. The cryosphere is clearly not just some distant frozen wasteland reserved for scientists and polar explorers.
Not at all. It is the operating system for the climate you live in.
Whether it is the melted mountain snow physically flowing out of your kitchen faucet, or the albedo effect determining the temperature outside your window, this frozen world dictates the parameters of human civilization.
Which leaves us with a fascinating and honestly pretty unsettling new reality to ponder as we wrap up.
Yeah, let's get into that.
So we've established that seasonal snowmelt and ancient glacial ice are absolutely crucial for our rivers, our agriculture, and our groundwater.
The global savings account.
Exactly. But the sources point out an unprecedented decline in Northern Hemisphere snow cover and mountain glaciers over the last century.
Right, they're melting faster than they're being replenished.
Yes. And because they're melting so fast, we are currently experiencing a temporary surge of water flowing down from the mountains. It feels like we have plenty of water right now.
But it's an illusion.
It is. So the provocative thought for everyone listening is this. What happens to global agriculture, to geopolitics, and to human survival when we finally hit peak water?
Peak water.
Yeah. What happens when that temporary surge ends and those ancient frozen water towers that have sustained us for millennia finally run completely dry?
That is a terrifying question. The tap just stops. Think about that next time you drop an ice cube in your glass or turn on your faucet. Until next time, keep digging deeper.